Okay, so I would like to thank the organizer for giving me the opportunity to present this work. So my title is about electronic spectroscopy of interstellar PAH cations and mainly photoproducts that are made in a gold ion trap experiment. And this work was done in particular for the spectroscopic part by my postdoc, Damian Kokin, and also the contribution of the engineer working on the setup, Anthony Bonami, and Giacomo Mulas, my collaborator on theoretical calculation. And I want to describe you a bit of the astrophysical scene, because I think this is something we have to keep in mind while doing experiment, because there are so many species we have to consider that and the experiments are usually very difficult. So we really need to think which type of species we have to deal with. And this is why in my group we are trying to get an overview of the evolution of interstellar PAHs, a problem of formation, but also UV processing, which I will describe, and which type of candidate will be favored. And then I will describe you more specifically the laboratory experiment and illustrate in particular what we can do in the laboratory, not necessarily show you the best interstellar candidates, but show you more the performances of the experiment. So we saw that already, just to remind you that PAHs were proposed as a carrier of the aromatic infrared bands that you see in many places of the interstellar medium where you have UV photon exciting their emission. And we had a lot of nice data from space mission, in particular the Infrared Space Observatory and the Spitzer Space Telescope. And from this observation, we could retrieve both spectra and also spatial information, so that we can study the evolution of these bands with physical conditions, in particular the UV fields in objects, which I will illustrate. So you can see these bands, which are broader than the typical ion line, which you see the recombination line, and also the rotational line of H2, which are of course more narrow. And you have these broader bands which are attributed to these aromatic molecules. So the model came both from the fact that since these bands are observed in emission, you need a mechanism that would trigger this emission due to the absorption of a single UV photon. And this is what we call the stochastic heating. So upon the absorption of a single UV photon, you get emission in all these bands, and this requires small system. Typically 50 atoms or around 50 atoms. That would bring your species to 1000 Kelvin, and then they could emit, because they're isolated, they could emit in infrared, including in the CH stretch, the 3.3 micron band. And the obvious candidate, because all these band positions are characteristic of aromatic bounds, CCH and CC aromatic bounds, are PAHs. That was proposed.
Why do you need 50 carbon atoms?
It's just when you calculate the heat capacity of your system, and you use a typical interstellar UV photon 10 eV.
Okay, so if you had a smaller system, you'd have a higher temperature.
Yes, exactly.
So you still have a lot of emission, right?
Yeah, sure. This is to give you an average size of 50 atoms, but this is in the original work, but you can have a distribution of sizes from the smaller one to larger one. Of course, when you go to larger system, you would emit less and less in this part and more at longer wavelength, because the system is colder. Okay? For a given internal energy, because you absorb a single UV photon.
Okay.
Is it?
I don't know if I believe that, but anyway, okay. Then I can get 1,000 is like red hot.
Yeah, 1000 Kelvin is when you, it's just the wind low when you want to emit at 3 micron. So it's 1000 K, because at 3 micron you need black body at 1000 K to emit. Okay? That was just a simple calculation in the original work. I'm just telling you the historical story. So in 94, 95, so Léger and Puget and Alamandola et al., they propose PAHs as a candidate. And when you make an energetic budget, so you estimate, well, you know how much energy is emitted in the infrared, and you estimate how much energy is absorbed in the UV. And from the energetic budget, you can retrieve 10 to 20% of total carbon in the galaxies included in this system, which make them really important system to consider in astrochemistry. So what you need to have in mind, it's a bit simplified, but it really tells you the story, is the photophysics of an isolated PAH. So you have the electronic state, so here a doublet state that would correspond to a PH cation, for instance, and you absorb a UV photon that brings you into an excited electronic state, and then you have fast internal conversion to basically the ground electronic state, in which you get a lot of vibrational energy, and then you have the IVR that redistribute all the energy within the vibrational modes, and then because the system is isolated, it can relax either by dissociation or by a slow infrared emission. So you have different time scale involved in this scheme, from the very fast internal conversion. Well, this is an idea of the lifetime. It doesn't mean it's the same for all systems, but to the slow infrared emission process. And then of course, you need different, you can use different theoretical approach to describe all these steps, to the statistical theories that we could use for the infrared emission and also for the dissociation. I will show you. So Olivier showed yesterday this scheme. So this is the idea that we have about the UV processing of the AIB carrier in interstellar medium. So this is the star illuminating the cloud, and you see the spatial distribution of different species. So further from the star, we have some very small grains that are the precursor of the PAH. Upon UV irradiation, they produce 3 PAHs. So we use as a simplified system PH cluster, but we could think of different clusters of different systems. And then you see basically a population of basically neutral PAHs. From the infrared spectroscopy, we can identify the spectrum more to neutral than to cation. And then you get closer to the star, you have the cation, and then even closer, you see the fullerene C60, C60+, and there's a possibility that here you have the hydrogenation of PAHs forming graphene sheets that would close and make the C60 as those proposed in this paper Bernier and Tillens. So what we are doing in the laboratory to better understand all these processes, so we built a setup dedicated to the study of larger carbon molecule, and in particular PAH. And the idea was to approach as possible the condition of the interstellar medium. So first, idea is isolation. So isolation from collision, so you need ultra-high vacuum, and isolation from thermal background, so you need a cold system. So the technique that was selected is an ion trap, more specifically an ion cyclotron resonance cell, which work by the action of a supraconductor magnet. So this is known as a mass spectrometer by many communities, but we built our own system because we wanted specific functionalities. Like for instance, once you have your ion isolated in the trap, you want to be able to study their interaction with photons. So we have a xenon lamp here that is focused by a mirror to the center of the cell. And we also have a tunable OPO laser and other UV laser, so that we can study the photodissociation, and I will show you the spectroscopy of the trap species. So the species were produced by desorption ionization laser scheme. So we have two lasers, and most PAHs were just like solid. So we make a deposit, and then we first laser, we desorb and make a plume, and then come with another laser to ionize the species. They are then guided by the magnetic field line and trapped inside the cell. And the analysis is Fourier transform mass spectrometry, which is also very nice because it's a non-destructive analysis. And it can be also used to select the species. So for instance, if you have different species produced in your trap, in your cell, you can isolate, you can eject selectively by exciting them in the cyclotron motion. Some of the species, so you can start with a single mass over charge ratio, so a single species, well, depending on the isomers, of course, but a single mass over charge ratio species. So, well, of course, what you would be happy is to have a synchrotron in your lab, but this is not feasible, so we are trying to use other techniques. So the first idea is to use the xenon arc lamp, so it's typically a solar spectrum, and you can use this lamp to build internal energy in your system. Because of the photophysical scheme I showed you before, you can absorb several photons and build internal energy in your system. So you see here, you absorb a first photon, you have fast internal conversion to the ground state, and then you can absorb another photon, and then you heat your system and get internal energy, and you can study the photodissociation. So this is what we did here on a coronene, this PAH C24H12. With the xenon lamp, and you have here the evolution of the mass spectrum as a function of the irradiation time. So it can be depending on how well you focus your lamp, or if you use filters, you can control the dissociation rate. So here we selected the carbon-12 isotope, ejected the carbon-13, and you start to see the loss of one H to H. So of course one of the questions is it 2H or H2? So this is something we also solved, and we found that this is mainly H by H dehydrogenation. The H2 production, if it exists, should be very low. And you see that at the end you end with the carbon cluster, totally dehydrogenated coronene C24+. So from the breakdown curve, so the evolution of abundance of the different species as a function of time, you want to derive information on the dissociation rate. So this is not straightforward. You need a model. So we used a Monte Carlo kinetics models in which we describe all the rates involved in the process. So we have UV visible absorption rate, infrared emission rate, and photodissociation rate, which we describe with a simplified statistical theory that is given here with the pre-exponential factor, AD, and the bonding energy, ED here. And you see here an example of, so these are a pointer experimental, and the curve are the fit from the model. And if you look at the, first thing is you cannot use all these parameters as, you cannot use all of them as free parameters because there's too many unknowns, so you have to make assumptions. So first, we notice that there are two dissociation channels, the one which involves species containing an even number of hydrogens, the one containing an odd number of hydrogen, which you can see here, but the species containing an odd number of hydrogen, they are much lower in intensity and they are photodissociated faster than the one containing an even number, which can be rationalized here, because if you lose one H here, you have time to lose one next to it, because you would build a triple bond, which is more favorable. So we have, so our plan was to assume that the dissociation energy for even H is known from previous experiment or from DFT calculation, and then fit the dissociation energy for the odd H, which we found here at 3.2 eV. And you see here on this scheme, so this is from the model, the dissociation rate corresponding to the H loss as a function of internal energy. And these are the two channels, the one which corresponds to an odd species and the one to an even species. So this is coronene basically, and this is coronene minus H. And this is the threshold energy. It means the energy at which you have competition with infrared cooling. So you see that you need typically 9 eV to dissociate coronene cation and less, like 5 or 6 eV to dissociate coronene minus H cation. And this is the result of the model as well, which gives you the distribution of internal energy in the dissociating ion. So you see the mean energy is given here for the different systems. We found that basically all the species of this form behave similarly, and all the species of this form as well. So, and you see that the threshold here is around 9 eV indeed. So it means that if you want to do multiphoton spectroscopy, you need to put 9 eV in your system to observe the fragmentation and then decide that it has absorbed, which make it more complicated. So from this work, we made a pH model for astrophysical environment. So we use what we know from coronene, and then we build a family of larger and larger molecules, and we scale the properties of coronene to the other species. And what we wanted to know is the hydrogenation and charge state of this PAH in space. So we had to include, of course, the reactivity and also the ionization and recombination with electron. And well, the problem with this model is, this is also the case for other models, is that there are many reactions that are poorly known. For instance, the reactivity with hydrogen. So this is basically a compilation of what's available. And you see that there are no measurements for pH larger than coronene. Well, okay, we can live with this in a way, but there are no measurements for neutral pHs, which is much worse. And also no measurement for superhydrogenated pH, because you could also have additional hydrogen, not other than the typical pH, what we call superhydrogenated species. So this is a summary of all the process. So this is ionization, recombination with electron. This concerns the dissociation. This is reactivity. So this in this table. And then we have to connect to the astrophysical conditions. So this is the same nebula as I showed before with the star and the cloud. And with models, we can describe the evolution of the radiation field while going inside the cloud, and also the evolution of the density, the hydrogen H2 density in particular, and the electronic density, and also the gas temperature, which we need for the model. And these are the results. Well, if you consider a pH small as a coronene, which is not so small, but you see that this is the hydrogenation state from 0 to 12, and this is the position inside the cloud. So here is the border of the cloud, and here you get inside and you have lower and lower UV radiation. And you see that there's no way here, they are all dehydrogenated. So we stop to C24+, but of course we have to consider also the possibility that C24+ could dissociate and leave to smaller carbon cluster, but we didn't in this model. So if you take a large one, but this is a large one, say C96, then you see that it is fully hydrogenated everywhere, and even it could accommodate extra hydrogen. So we consider only one step. So we stop here because we have no data after that, but it could be more. And then you have the intermediate cases, which behave sometimes a bit funny, but it depends on the competition between photodissociation and reactivity with hydrogen. So this is why you see this bimodal behavior. But what was a surprise to me is that you don't expect so many partially dehydrogenated species. Or you're fully or superhydrogenated, or you are completely dehydrogenated. So that was a bit surprising in a sense. Well, this is the result of the model, but certainly we have to learn from such model. So as a position inside the cloud, you see that you can have either carbon cluster for the sizes below 50 or 60 carbon atom, which would be good for the C60, by the way. And you have the pH, then more like typical pH pieces, and then superhydrogenated pieces for the larger. And also because the reactivity is induced by atomic hydrogen, and atomic hydrogen is present only is more abundant at the surface of the cloud where H2 is dissociated. When you get inside, you have more H2, and it would depend on the reactivity with H and H2, which you see here. Here we consider a higher value for the reactivity of H2, and here we consider that there was no reactivity of H2. So you see that the border shifts a bit. Okay, so now I go to the experiment. So the motivation, well, we heard from Tim already that one motivation of this experiment is the connection with the deep problem. So we want to, in our experiment, what we think we can do is investigate candidates that are photoproducts, which might be good candidates for the deeps. But we can work only on ionized species because of the trapping. And the question is a spectroscopic scheme we can achieve in our experiment, which is a multi-photodissociation scheme, is appropriate for interstellar conditions. But we can also use electronic signature as diagnostic of the evolution of the structure with the hydrogenation, clustering, and also complexation with metal, which are of interest for us. And we can investigate also isomers, because if you have a M/Z ratio, it doesn't tell you anything about the structure, but if you can combine with spectroscopy, then you can learn something about the structure of a species. So again, the experiment, so in this experiment we use the OPO laser to photodissociate, so it's typical from near UV to near infrared, but what I will present is essentially the visible part around between 400 nanometer and 500 nanometer. And we can combine, I will show some experiment, another UV laser to get a two-color scheme. So one candidate we studied, of course this is not the sizes, this is not C96, so we started with much smaller, is methylpyrene, because it was proposed some years ago as a possible candidate for the famous 4430 angstrom deep. And actually a photoproduct of methylpyrene was proposed. So the experiment here made in neon matrix. So you isolate methylpyrene in neon matrix, and then you irradiate with a hydrogen discharge lamp, so mainly with Lyman alpha photon, and you observe some bands like A, B, D, which rise with the UV radiation and which would correspond to possible deeps. So in our setup, we started with a spectroscopy of one methylpyrene cation. So you see here, so we start to play with the laser condition to try to optimize the spectroscopy. So you see here with the OPO laser only, so it's a one-shot experiment. So you send one shot and look at the photodissociation of species. So use here 1 millijoule of the laser and 2 millijoule, and you see the dissociation fraction here, which is up to 70%. And these two sticks here correspond to the theoretical calculation, the TDDFT calculation, which show that there are two possible isomers This one given, well, it is called F and E. It's not the proper name, but it's just in figure. It was F and E species, but there are 2 isomers. So this one, you see the position of the CH3 group. And actually, on this scheme here, you can see that you have 2 bands, one here, and then some vibronic structure. And you see it better here. So I shifted a bit so that you can make the analogy between the main isomer here and the other one here, and also on the vibronic structure. So apparently two vibrations around this frequency were observed. So next step is to look at the photodissociation products. So using the xenon lamp, we dissociate methylpyrene. So methylpyrene is mass 216, and we have 2 main products. So if this is 0.5 seconds of the lamp, you see 215, so 1 hydrogen loss, and 189, which is a further C2H2 loss. So these are the structures that have been calculated. So this is methylpyrene, and this is a species -H. So you have 2 possibilities. Either you have this methylene group, CH2 group, or you get a 5-member ring here. So you can see the corresponding energy here. And this is a product of a C2H2 loss. So, well, the spectroscopy was not so beautiful in this case, but I think we got some information anyway. So here for 215, we actually observed two bands. Well, they look broad, but actually it should be scanned at a bit higher step, but they are broad intrinsically, I think. And they correspond quite well to the 2 bands predicted for the 2 isomers, which is good. And what is also nice is that you see from methylpyrene, and for this species as well, you observe typically bands with an oscillator strength of 0.1, 0.2. So this is consistent. And the one at 189 has an absorption which is more in the near UV, but you start to see the rise here, and this is the theoretical band, so everything seems consistent. So then we went to a larger, our favorite pH, coronene cation, which is larger and require more energy to break. Just before, I forgot to mention, no, this was only performed with 1 laser experiment, so only with the OPO laser. So now we are going to see if we can implement a 2-laser, 2-color scheme. So in red is the spectrum we have in neon matrix that has been a bit blue shifted to better fit gas phase spectrum. And is black is what we could measure with the OPO laser. And you see here we need 15 millijoule, which corresponds, because 9 eV or more, it corresponds to the absorption of 4 photons. So we need to put some energy. So 4 photons within laser pulse. Nanosecond laser pulse. It's not 4 photon, it's not a multi-photon, sequential absorption of photon within a laser pulse. And this one, so the red one here corresponds to the black one here, and the blue and green were tentative to combine the OPO laser with the UV laser we have, which is a YAG, a quadruple YAG at 266 nanometer. But unfortunately, this UV wavelength is not enough to go to 1 photon for the OPO, which we would like to. But still, you start to see that the band is getting a bit sharper. And here, in the green one, we also achieve to get a sharper edge, I think, because we increase the cooling of the ion in the trap, because we are using buffer gas. we cannot use millibar of buffer gas. It's impossible with this kind of experiment. But we can increase a bit, and we actually here you have five times more gas, and you actually see that the threshold is better defined. So clearly there's something to do on the cooling of the ion, on the multiphoton scheme, but still it will be difficult to get to this band measuring matrix. It's really tricky. Another species we studied, which is of comparable size, is naphtho-pyrene cation, which is this guy here. And you see the band here. And actually, you have two bands which are predicted by theory. So I think you have the two bands here. And you see again that the band, well, you have quite broad bands. And here we had also a two laser scheme. But in general, all these systems, they have broad bands, a few hundred wave number, and they are not good deep candidates. This is what we can conclude. And increasing the size, I don't think it would help from this point of view. So the advantage of our technique is that we can produce in situ some photofragments and control them because of trapping and ejection facilities. So that provides good indication of the band position. Well, our laser is not, the resolution is not fantastic. It's like maybe 0.5 nanometer, but still it's really good. It really gives a good indication of the band position. Disadvantage, it's really hard to get to the profile of the cold ion band, but still we can see that they are broad intrinsically. So. And broadening can be due to different reasons. Some are due to the experiments or the preparation of ions and the cooling. Is it enough? The buffer gas cooling is enough. And also to the multiphoton absorption process. But also there's this lifetime broadening due to fast internal conversion, and this we have to live with. And comparison with theory, TDDFT is quite good. Well, predicted band position are better than 0.2 eV, and there are all the band we studied are blue shifted in theory. And oscillator strength are in the range 0.1, 0.2, the band we observe. And we have a difficulty with coronene plus because of symmetry, Nyan-Teller effect. So there are calculations in both enforcing the CH symmetry or relaxing to D to H. So this one is better, but still not enough. And in particular, the band position is kind of okay, but the oscillator strength, I think, is wrong. Cannot be 0.01 or 0.03 because it would be really hard to observe it in our experiment. So there's a current effort from my colleague Giacomo to calculate the vibranic structure using higher level calculation. And so current studies is to study C24 plus, produced either from coronene or naphtho-pyrene. So our idea is to test whether you keep the pH skeleton or you isomerize into some different like ring structure or closed structure. But so far we haven't seen any bands. And this is consistent with theory because this carbon cluster system, they have many electronic transitions and none of them is strong. So this would be difficult to do, I think. That would be nice, but this is difficult. And we are also working on the spectroscopy of the coronene dimer cation because we are interested by the properties of this carbon cluster, of this pH cluster as candidate for the very small grains. This is some first experiment in which we produce. So we have we produce them in situ in the trap. So we have a coronene cation trap here, and then we have a small oven, and we evaporate a vapor and make it react at low pressure. So we can build the dimer, the trimer, but not very big one. And so you see here the dimer at mass 600, and which evaporate with the lamp to produce back the monomer. And we are now trying to record the spectroscopy of this guy. So just to finish on the astrophysical implication, I think that pH cation and photoproducts are likely not good candidates for the DIPS, at least the ionized one. And so how to identify interstellar pHs, that's a problem because mid-infrared range is not specific enough. We have family of species, so we cannot identify individual species. Well, C60 was a counterexample, but this is really because it has a very specific infrared mode. So our idea and others is to go for the far infrared range, but because you have specific vibrational modes there. But this is very challenging. So there are efforts now to identify in the air shell spectra some of these bands that are predicted by a model, but they're expected to be weak. So I don't know. We are working on this, but I cannot say today what will be the chance to detect some of them. But at the end, the main conclusion is how can we really identify this interstellar pH? Because if we have no identification of a single molecule, then it would challenge the model in a way, although it can be understood. The reason why.
I'm sorry, so at the top there you say that paper says that there's emission of 40 pHs?
Yeah, well, this is a simulation, okay? Here.
Okay.
It's a simulation on small pHs,
Yeah.
well, up to a size of maybe 30 carbon atoms, including both neutral and cation. It's just to illustrate that when you are in the mid-infrared range, you have all these bands falling about at the same position.
So this is just one possible fit, but you say it's not conclusive at all?
It's not a fit, it's a simulation. It's just a simulation. It's an emission model that include...
Is there any experimental data on this plot? Or?
No.
Oh,
it's
okay.
a simulation. Yeah.
I can see that.
And then it uses a database on pH properties, which are actually mainly theoretical properties. So no, it's an emission model in which you include the radiation field of the star, which is a red rectangle here, and you absorb photon given the absorption cross-section, and you emit photon with an emission model, as Jan discussed also for C60, all this emission model. Just to illustrate that when you go to the far infrared range, you expect some isolated bands which are specific of some molecular structure. And if we can get one of these and analyze the rotational structure in the bands, an harmonic structure also of the band, we can learn a lot about the molecule, and it's a possible way to identify these pHs. So. Okay, so I just want to analyze a few more people. Julien Montillo, former PhD student who did most of the work on the chemical model. Aude Simon, who performed the calculation on methylpyrene and derivative, and the technical team of the PIRENEA setup, and financial support by various sponsors. And thank you for your attention.
I was explaining to you a while ago that we have to end the session at a specific time because I guess someone else will be using this room. But we can cut into the coffee, I guess, what, a couple of minutes. We have to begin the next talk at 10:30 sharply. So there are a few minutes to, yes.
So you concluded that the pH is not a good candidate for the DIB.
Cation analysis.
Because the bands are too broad? Is that what you mean?
Mm-hmm.
Did you ever consider small ones?
Small pH.
They have narrower bands?
No.
It's too big.
It's too big also, yes.
16 wavelengths. So.
Well, neutral pHs, they have narrower bands. The neutral one.
So neutral ones are still possible candidates for DIB?
Yeah, but then you need to go to the large one, neutral one. Yeah.
Why does it have to be large? Because that's what I don't understand.
Because of the stability. I really think we need to consider large pieces. I would not look for naphthalene as a carrier of the DIB.
Right, right. Okay, but it's because in your experiment you have very high photon flux.
Well, the large one, there's another reason, is that the neutral, they don't absorb the small one, they don't absorb in the visible, they absorb in the middle, right?
Yeah.
Yeah.
But they don't have to be so large.
Hmm?
I mean, there's still pretty small molecules that are dyes, for example, that absorb the invisible.
Yes.
So it doesn't have to be as big as coronene to absorb the coronene.
Yeah, they should be as big as coronene, even bigger, yes.
I mean, you show the coronene is plenty big enough, right? You have absorptions right in the right region.
Cation, yes, but not the neutral.
Oh, no.
Yes.
Okay.
This is really quite interesting. So, have you or have other people been able to ever sort of look at a case where you could maybe make I don't even know if the doubly charged cations are stable, but how did these spectra shift between, let's say, monovalent cations and divalent cations? Has that been demonstrated in these larger sorts of
You mean the evolution of spectroscopic properties?
Yeah, right.
This has been done by TD-DFT and DFT calculation, yes.
Okay, so just by calculation.
Yes.
All right, which is fine.
The problem with the dication is, well, you could have some in some specific region. Otherwise, you are more in the balance between neutral and cation. Maybe some anions in some cases, but the two main populations is more like cation and neutral.
So maybe it's not of interest to you as a candidate for the bid, but is there extraordinary sensitivity to the charge state in terms of what the spectrum is, or is it? Are you still small enough, or maybe are you large enough so that having it be singly charged or doubly charged would not make much difference?
Are you talking about electronic or,
Yeah.
or infrared properties?
I'm actually interested. I imagine the infrared isn't going to change too much, but does the electronic spectrum shift dramatically with charge state?
Yeah, sure.
Well, okay. So,
Because already from neutral to ionized, you remove one electron, so you make a hole. So you allow some transition which absorb in the visible or even near infrared that are not observed in the neutral. So when you remove a second electron, then you change again, and well, dication can be closer actually to neutral than to cation in terms of well, it's
not entirely so obvious. I mean, many people will do spectroscopy of metal clusters, and they'll basically say that the electronic spectrum of the metal cluster is the same for negative anionic cluster or a neutral cluster or a positively charged cluster. So, in some sense, it's a matter of how big the system actually is. But apparently, in these systems, you're still in a region where it's sensitive to the
yes.
charge state, in sort of, like as you say, electron hole pair sort of sense.
Mm-hmm.
Can I say a second question? When you excite with your arc lamp, okay, and then you were really having essentially sort of a multi-photon process. You were sort of exciting and then letting it undergo internal conversion, and then exciting again.
Yes.
Okay? And that's how you had the beautiful time zone, 20 seconds of illumination or whatever. So how well, I mean, in order to be able to understand that process, one needs to be able to understand the relaxation processes that are competing with this.
Yes.
How well do people understand? I mean, is that relaxation? Is that mostly infrared radiation? How well do they understand the radiative properties of these?
Yes, it's actually true that we still have to learn about the relaxation processes. Infrared cooling is one way. Another way is electronic cooling, which I completely I didn't discuss it at all.
Electronic emission.
Yes. There's a direct fluorescence that everybody knows, but there's also another process which is due to the which is due to the hot electron in a way relaxing, because when you do the infrared emission, you consider vibration, but you forget about electron, right? But in fact, it is mixed. So you can have reverse transition to excited electronic state and then emit an electronic photon from an excited state. And this has been observed for C60, for instance. There are a lot of studies on this. So if your system is hot enough, so in our case, for the cation, this is what we call the Poincaré fluorescence. There's a paper on this. And it starts to be observed in experiment. In storage ring, they can measure the cooling due to this kind of electronic emission, which occur at smaller time scale than infrared emission. It's more like millisecond or lower.
In your ICR, though, you think that your ions are cold, or reasonably cold? I mean, like at least below room temperature or something like that?
Yes, yes. Well, the trap, I haven't this. Yeah, I forgot to mention the temperature of the trap is 30 Kelvin. Doesn't mean that the ions are at 30 Kelvin. And then we use a buffer gas to cool the ion. But I don't know what is the exact temperature of the ion. It's complicated. And since we cannot use high resolution spectroscopy, I don't think, formation of van der Waals complexes is a way to test temperature. But so far we didn't observe complexes with argon, for instance. So they are not so cold, but still I think they are way below room temperature. We recorded some of the spectra, like the coronene one, at room temperature, and we actually observe a broadening of the band. So we really think there's some cooling, but how much is difficult to say.
In the slide where you showed the estimated rates for a lot of reactions with H atoms and H2 and so on, and then later you have a model that has effectors. The effectors are are orders of magnitude different in your model than those numbers that you quoted. I assume that must be because you're including a lot of other effects about the radiation.
Which you are talking about the H2?
You have a table.
Like this one?
Yeah, so you have all those numbers of the radiation. So the top you said the reactions with H. So that's
yes. And the reaction with H2, there's no...
Okay, so forget the H2, but just the H. So you're doing the reverse of that process in your experiment, right? You're
yes.
You're spitting
yes.
out the H. So
well, actually, yeah. Actually not, because the only measurement, the measurement is this one. Yeah, okay. But these are extrapolation from experiment on other systems.
yeah,
you
sure,
see, this is
sure.
experiment.
But they're all about the same order of magnitude.
Okay.
So your numbers will be somewhere in that order of magnitude if it was a thermal experiment.
Yes.
But your experiment is not. You're having a very unusual energy distribution because of the radiation.
Yes.
So then when you made your model, you have numbers that maybe it was
This one?
Yeah. So then the A factors now are 10 to 17.
Wait. These are for the neutral, and these are the cation. You have to be careful because the measurement, as I said here,
Yeah.
the measurement are only on the cation, and there's no measurement for neutral.
Okay.
So what we expect is the reactivity for neutral would be
Okay.
less, but
Okay.
so this is why there's a range here.
Right. I guess I was looking at the column, the A is one column over has A factors. You're reading as A factor.
This one?
Yeah. So those numbers are very high.
Yeah, but this comes from the formula here, right? So then you have to calculate the density of states.
So,
Okay.
so it could be the density of states calculation. Well, there's several possibilities. The U also depends on, right?
The U is the internal energy in your
Yeah,
system.
which is very complicated because you have.
No, but you calculate it for each. You calculate it for each internal energy, as shown here. So for each internal energy,
Right.
that should be U here. Sorry, if it's
Yeah.
U here, okay.
But
You calculate a specific K
but I think you
dissociation.
don't know the U in that your molecules have in your experiment is not it's not perfectly clear.
This is simulated from the absorption of photon, because we use this Monte Carlo model in which we describe the lamp spectrum and
Yeah.
flux, and we also know the cross-section, absorption cross-section of the ion.
Right, but the process is, it's a multi-photon process, right? So you absorb this photon,
Yes,
but then...
but the Monte Carlo follow all the events.
Right, but you don't know the numbers for the Poincare emission and the infrared emission.
Ah, well, we tune them in the model. Yes, yes. Infrared emission, we know.
So there's correlated parameters in the model.
So the Poincare emission is not important, because here we are at the threshold. We are around the threshold, and the Poincare is not so important,
Okay.
because you need more energy. So first question. Infrared emission, we know how to calculate it from...
But it must depend on the anharmonicity, because what you're doing is emission of combination bands. Right, you're forming...
No, we calculate the population of vibrational bands, and
Yeah, but what transition dipole do you use for the...
you use one from the
fundamental.
DFT calculation.
for
Yes,
the
yes,
fundamental?
yes,
Yeah,
yes.
but you're way high, so the transition dipoles will be electric.
Yeah, this is not bad. No, this works pretty well.
Well, like the Highland dot he measured for the, he did the same experiment with maybe pyrene.
Yeah.
He excited it, and then he measured the infrared emission with time, and you can see it changing.
You're talking about Sekali work? Or who?
Highland Dai, D-A-I. He was professor at Penn. Now he's at Cations.
Okay. So he did what? The simulation? Well,
No,
in
no,
Philip
no.
group, they're simulating this,
No,
taking into account all the combination band.
It's a real experiment.
An experiment.
So he excites it with probably 1 photon of UV, and then he just watches the dispersed fluorescence with time from that one molecule. And so you can see the intensity and the frequencies emitted.
Okay.
And it changes in quite
Yeah,
a complicated
sure.
way.
Sure.
So that's, but I would say that for sure the intensity is not exactly the same all the way down.
No, of course. In absorption, yes, but not in
No.
emission.
Yeah, emission, yeah. So the infrared
Yes.
emission part I think is very
But you take this into account, yes,
But I think we don't know
through
what
the
it is for-
population of state.
Yeah, but I mean, I feel like we don't know what that number is for coronene ion. I mean,
You can yeah, well, you have a good estimate in the harmonic approximation, but I think it would not change much, because well, it would change the value of the infrared cooling, which I haven't seen, but it's basically like flat, you know, like a value of 5 per second. It rises a bit at the beginning, and then it's basically flat. So, and I don't think it would change a lot.
Okay, but then we have a problem because the model has an unphysical A factor too high.
No?
Yeah, you're
I
definitely.
think we
Yeah,
have to
okay.
adjourn for
Okay.
coffee. Maybe you can continue the discussion.
Yeah, it's too technical.
No, it's very interesting. It'd be nice to continue.